But yes, I'll give more guides as I go through the presentation for you to have a better understanding. Let me share the screen. I'll share the entire screen so I can move around. Okay. I would need the confirmation, I guess, dismiss. Well, I would need the confirmation from you guys if you can see my screen now as I'm sharing it, the full screen or not.
Yes, we can see your screen.
Great. Perfect. Okay, well, welcome everyone. Thank you for joining. This is too exciting. Sometimes the online workshops are not as, let's say, interactive, I would say, because I just see my screen and I don't see any other person in the room. But seeing all of the list of the people on the chat was amazing before I shared the screen. So that's great. Today, I'm going to talk about the scale of history on account abstraction. And before diving in, I am Albiona. You can find me as Albi Codes, or I go by Albi, my short name, everywhere, but my socials have the Albi Codes username. I am a DevRel engineer at Matter Labs, and I'll give like a mini introduction about my career, since maybe like all of the other attendees might find it inspirational, or like just are interested to get to know why am I here and how did I go through my career. So I have like around 3 years of experience in software development, mainly focused in front-end development. And then I moved to developer relations side like 4 years ago, and I've been doing it consistently. And I joined Web3 like 3 years ago. For a privacy protocol at the time as a DevRel, and my only like encouragement was for like based on cryptography and mathematics. I was very passionate about maths when I was very young, and I just decided to kind of navigate and be around projects or protocols that do tend to have some math in them in a way or another. That's how I kind of joined as well Matter Labs closely 2 years ago. So yeah, that was it. Do send me DMs or something, like tag me anywhere you want to connect on socials. I'm Albico's Telegram or Twitter, and as well as Instagram. So what is the progress to onboard a billion users, the next billion users, right? What are we doing for a normal average person in the world to join the vast ecosystem of cryptocurrencies, decentralized applications, and NFTs? Onboarding people to blockchain and decentralized finance, it takes like one long action for a person to do, and that is creating an externally owned account. To create an externally owned account is crucial, and is like the key point where it kind of allows people to join this vast ecosystem, right? But to create one and be able to navigate through the ecosystem, it's a pain for the user perspective. So to onboard this next billion users, let's review this process, what it takes for a normal person to be able to join Web3 and interact on chain. So first things first, this is the user overview, right? You want to download an app that allows you to create an account for Web3, and you want to be this application from very secure sources so that you're all good set up from the beginning and be aware, right, for the security perspective. You download the application that provides you for the option for you to create your wallet. And while you create your wallet, you will be going through different processes where you will have to set up your passwords and verify your identity and stuff like that. And then after, you will be given a seed phrase, right? A long thing that will be used for you to be able to access your wallet, even if you lose different passwords for different accounts, because as we know, we can create multiple accounts in one wallet. The crucial point in here is that you need this seed phrase to be saved or stored somewhere physically so that you're able to access back to your funds whenever you use any kind of password. When you create your account or your externally owned account, then you need to verify your address, going back and forth with some steps, and then you need to take that address, wallet address that now it's yours, for you to be able to interact with on-chain or like receive funds and stuff like that. For you to be able to interact on-chain, now you don't have, if with a freshly new address, you don't have any funds. So you need to go and to provide this address for you to receive some money in this address. You receive this money, let's say, from a friend or whatever. We are not going there. And then you go to Uniswap and you want to do some activity on there, but you have only USDC in your wallet and you have no ETH for the gas to do the transactions. So you go back. This is where you're like, oh, I need to also get some money out of my bank to ramp to fund my gas. So you go back, you get some money, you buy ETH, and then you want with that ETH to fund the swap, right? Then you send that ETH to your account, you go back to Uniswap to do that swap from USDC that you have received earlier for ETH. And then you go back to the interaction on chain, let's say OpenSea, to buy an NFT. But there you learn that, oh, you actually need to buy the NFT with wrapped ETH, but you don't have the wrapped ETH in your wallet, right? So now we take a deep breath and we're like, okay, wait. If we are lucky, we have gone through 13 steps in like a day, which is not the case for someone who's touching for the first time an externally owned account, an application, a seed phrase, saving it up somewhere, getting real money, putting that into like an account that you don't know how it will go through because you don't know even how to use that money, etc. Right? If we didn't give up from all of these steps, then we will go back to Uniswap and wrap all of your ETH, like in wrapped ETH, swap it up, and then you go back to Uniswap, but you don't have actual ETH for gas because you forgot the fact that you need the gas in ETH to pay for the NFT buying transaction. This was an overview of all of you, maybe what you went through early when you joined Web3, or even now what you're going through. And this process is too exhausted for everyone. Now imagine it was extremely exhausted when, for me, when I was going through this thing, and even though I was like a developer, I thought I was like, okay, this is easy, but the money perspective and the value that it has, it's actually like, it takes energy from you to do that. But yes, as we went through the overview from the user's perspective on account abstraction, in here we will kind of see what do those two accounts, externally owned account and smart accounts, differ between when it comes to the technical perspective. So externally owned accounts are very easy to set up. Outside of that user experience, they don't cost any money for you to create an externally owned account. You can initiate transactions in ETH and all of the other ERC20 tokens. And transactions between externally owned accounts can happen, like an externally owned account can only send transactions to a smart contract address, but cannot like do something. Later on, we'll review what does that mean. And also on the security perspective, an externally owned account is made up by the cryptographic pair of keys, such as the public and private key. And those two are very important that keep up your account security in place, that you need to kind of use them for different use cases, right? And then smart accounts are code-based smart accounts created through the account abstraction implementations that are different in different protocols. Creating a smart account costs because we need to do network storage on a protocol like zk-sync in this case. And then to initiate transactions from a smart account, we can't do it like automatically, let's say. Those will be initiated if we receive a transaction from externally on the account. Let's say your main externally on the account, you go and you develop a smart account with zk-sync. You need to initiate a transaction from this externally owned account for you to be able to unlock the execution of some kind of function. So externally owned accounts can send transactions and can trigger code which can execute different things like token transfers, contract creation, swaps, limits on the account, and so on. So there are no keys to be controlled for the smart contract accounts, but the code that you actually write will control the funds and everything that happens in between. These are some of the limitations that the externally owned accounts have. In this case, when it comes to security vulnerabilities, the security is all based on human efforts, like saving a password or keeping the node somewhere physically that you can access it no matter what if you lose all of your devices or something like that, so that you can kind of go back and be able to access it. There's a big opportunity for human error, right? And then the private key management is also the same. There's limited functionality. You only do one transaction at a time. Like imagine if you scroll through social media and all of the posts that you see, all of these would be all of these calls in the backend would be transactions on a Web3 perspective. Well, maybe not all of these, but any interaction, liking, posting, and stuff like that is like another transaction at a time. So with an externally owned account, you can do one transaction per one click or whatever, signing it. So it's like, oh, but what does that mean for the actual onboarding or millions of transactions where you can kind of go through an app and use it, right? Then usability and the UX, as we repeated when it comes to the user experience, the scalability issue, manual transaction signing and no native multi-signature implementations for managing one externally owned account. And when it comes to the economic limitations and transaction fees, even though transaction fees went down with the blobs integration, actually there is in the context that I mentioned earlier with millions of transactions, let's say for a city to work on blockchain, then yes, the transaction fees are a limitation. But this is a continuous work that is happening in different perspectives, and also with the zk-sync, there's always upgrades where you can kind of we are lowering the gas for users and devs. So how did the account abstraction even came now live, or how did it happen for us to be able to have a smart account and develop these, make them programmable? It actually started way back in 2014, 15, 16, when Vitalik proposed EIP 86. And the goal was to enable users when they join Web3 to actually have some value or no addresses when they join in a way or another, but it was not successful due to the implementation reasons. And then the EIP 101 in 2016 was also trying to make the externally owned account more smart in a way, but it didn't go through. And in this pipeline, I've included the actual zk-sync development and what happened during the years. In late 2019, zk-sync 1.0 went live, and it offered only payments and swaps in different currencies only. And then the EIP 29 4338 came up in 2020, which is very close to the 4337 that supports the native implementation of account abstraction on the Ethereum protocol. And then we have zkSync 2.0, which came by mid-2021, and the 2.0 was able to actually have EVM compatible, meaning we would extend not only scaling the Ethereum transactions to have more transactions per second and like onboarding more people, but also being able for developers to actually build on top of zkSync with additional features that I'll mention later, and also benefits that they would kind of enjoy from Ethereum as well. In late 2021, zkSync announced the native implementation of account abstraction, and then EIP 4337 came up in 2023, together with zkSync native account abstraction in 2023, which both were launched during ETH Denver last year. And with the significant difference between the two when it comes to the transaction flow, and also we went live on mainnet. At that time, we also had an in-person account abstraction like implementation. If you would be like an attendee, you would get BITL tokens, and then with those BITL tokens, you would buy your food to eat from food trucks, and you would not do any. There was no gas fee for you to pay. Only like 10 BITL tokens for 2 meals, let's say, and that's it. You would just go scan a QR code, and then you'd be able to get food. So what does the account abstraction enables, right? Different features such as social recovery, meaning you have a family or like friends where each of them has some specific part of password that when they all bring together their pieces, you can actually recover your account. You have the spending limits or spending rules where you get to limit the spending interactions of your accounts in different ways based on the use case of, let's say, browser interactions that you do, then your Hot or like wallet that you do, or work-related transactions or whatever, right? And then it's flexible validation, signature schemes now with different 256 R1 curve that is also implemented in the protocol level on zkSync. You're able to build a smart account that you can sign up with your Face ID or your fingerprint on your phone, or things like that. And then you can have multi-call and sessions, meaning when it comes to the gaming use cases and you want to, for the next hour, to do multiple transactions, you just enable that, and then whatever transaction happen in the specific limit, they can go, right? They can be successful. And then as well, the last but not least, the multi-token gas, where you can pay gas in any ERC20 token. So you don't have to have ETH in your wallet, as we saw in the user experience of the externally owned account. And here we see the EIP 4337 implementation, which introduces a new transaction flow for smart contract accounts. The difference between those are seen in like two parallels, right? There on top, we have an externally owned account, which all transactions collected on a mempool. Then you have the node or the validator, which gets those and submits them to Ethereum. And then a contract account or account abstraction contract. The code gets written, all of the transactions are collected from the user ops mempool. Then those get collected from different bundlers, in this case for 4337, which are like different external party bundlers that do the work. They submit those into an entry point contract, where this entry point contract can then be connected with a paymaster, optional or not, and then be submitted to the Ethereum layer 1 network. And then the difference between that flow and the native account abstraction on zkSync Kira is this. Each externally owned account is a smart contract account. What does that mean? Is that even if you have an externally owned account on your MetaMask and then you bridge to zkSync era funds, and then with those funds you want to kind of build a smart contract account and everything. The account stays the same, but it has more functionality on zk-sync era network. The transactions that get initiated by both types of accounts are unified into the mempool, which then are collected by the operator. In this case is called zk-sync, and then after the operator gets them, we have like an entry point contract that is called at 4337. We have the bootloader contract that collects all of these transactions, and then that's where we have a paymaster optional parameter, where if the transaction had some specific parameters that enable paymasters or not, and the type of paymaster, it will be activated. If not, it will then be posted on chain. Today, what you can do, we have like around 400 days being live on mainnet. And what can you actually do on zk-sync? We have different applications that you can go through and test around. Each of these offer different features. Some of these, for example, offer you like zero fees on ETH only. You can pay like on USDC or any other token type, and those are categorized in DeFi, gaming, wallets like Clay Wallet that I would suggest for you to kind of check out, because it's very good in the user experience of you kind of signing transactions with your Face ID and stuff like that. For you to be able to implement on a smart account on zk-sync, we have an interface which is called Account Interface. This is called by the bootloader to validate that an account agrees to process the transaction and potentially pay for it. When it comes to the word an account, is that this Account Interface, when you go through the tutorial, you will see that you will be able to build not just one account, you'll be able to build a factory contract that can initiate multiple accounts. And that's where this is called when it comes to the bootloader validates the transaction and sees if the account will pay for the gas fees or not. The use cases, as I mentioned earlier in this case, that you can actually implement on the contract code level is that you can have different signature validation signatures for transactions, and you can be initiating different actions based on those signatures. And we'll see a little example by the end of this, where we kind of change the signature of the account. There is native multi-signature wallets where you can have multiple signature being received, like coming up to the wallet and then having some action taking place because multiple signatures happened. And then we have the identity contracts, authenticating users, like identity verifications through the contract code, right? These are the 5 different functions that make an account interface for you to be able to walk through. And this is kind of the transaction flow, what happens when it comes to the account abstraction. The validate transaction, that is the first function over there, does a couple of very important things, such as increments the nonce of the transaction, checks for fees, and verifies the signature. And then those get passed to the execute transaction function. In this case, you can see the 2 different parameters on the code, transaction hash and suggested signed hash, and the transaction as well. This forwards transaction and value the destination contract. And then when it comes to the paymasters feature enabled, right? The function pay for transaction is optional. It can pay transaction fees, pays transaction fees to the bootloader, or the paymaster in this case pays for it. Preparing for paymaster is optional. It gets the paymaster parameters and then it calls helper functions such as process paymaster input and moves forward to the execution side. Then we have the execute transaction from the outside, which is optional as well and allows executing transactions by other entities. For example, non the bootloader. When it comes to the flow that I explained earlier, in this case, the bootloader is one of the entry points contracts, let's say, called in the 4337, which is responsible to get all of the transactions and move them on-chain. Validate transaction, this function will dive deeper into this. We mentioned that it increments the nonce, it validates the transaction hash, it checks the balance, verifies the signatures, and handles signer type. This handling the signer type emoji in here is something that is a use case in this example. This is not a default example. This is what I mentioned earlier, that we will see how it is when it comes to us changing the signature type for us to include an additional byte. The function examines the first byte of the signature to determine the signer type. And then if the first byte is 0, we call a function that is called check restriction. So all of this part here, handling signer type, is a use case that I'm kind of walking you through. When you go through the validate transaction in this case, you will see different things happening, like the nonce account increase, and then the suggested signed hash in here, we see if the this is equal to this length byte, etc. And then we check the total required balance in this line. And when it comes to the byte, the first byte of the transaction, as you can see in the beginning of the function, one of the parameters is the actual transaction itself. And the first byte that we are changing, in this case, we are not changing, we are just checking if the current transaction that came has a first byte that is different from any other type of transaction that we would receive. We are just checking. So the transaction dot signature in the place 0 is the first byte, and then we have an if method here. I don't know why I cut the image so low there, but yes, the first byte here is the if it's 0, it will call the check restrictions function, which then we'll see what happens, or like we'll be free to be like, okay, if this is 0, this is coming from a hot wallet. On the hot wallet, then let's do these restrictions when it comes to spending limits, right? For us to be able to change that signature, for us to be able to actually have that first byte of the signature 0 or 1, right? Because that is not fundamentally as it acts default, right? The first byte is not allocated to us in this case. And also the actual use case, because I forgot to mention, is we want to see if a transaction is coming from a hot wallet or a cold wallet. If it's coming from a hot wallet, then we need to check restrictions, etc. So how did we change the signature? The ECDSA signature is the elliptic curve signature algorithm that helps us to make this Ethereum externally owned account secure, right? Is essential for ensuring that the security and the integrity of the message on Ethereum is there. This is a cryptographic algorithm used for digital signatures, that kind of signature that we receive. The curve itself is like the curve calculation that is done for Ethereum is called SecP256K1, from which we extract different values. And while we extract different values from that curve, we are able to modify the signature itself. So the ECDSA signature, this is wrong, sorry. The format of the ECDSA signature consists two integers, R and S, plus in Ethereum an additional component V, which is used for recovery ID. The format then includes three different types, the R, S, and V. The R and S are the ECDSA components. The V helps to reconstruct the public key. Use cases in this ECDSA signature are that we use this algorithm to verify transactions sent by user wallets and to verify the authenticity of the messages. This is an diagram of how the ECDSA signature works. The user, when they initiate the transaction from the Ethereum wallet, the transaction goes from the Ethereum wallet and it gets hashed with the data, like the data that we are sending, whatever value that we are signing the transaction for, etc. That data gets hashed back, and then we provide the private key in this case to be able to enable for this data to go forward. With that private key, then we have the hashed data, that the value that we want to send via transaction, plus the private key to the ECDSA, and then we get the digital signature for the hash data together with the private key. Now that we have the digital signature, we send it back. We send it to the blockchain, and then we verify and accept the transaction. So it's like we get the data, we provide the private key, we get hashed data and the private key. Then together with those, we create the digital signature through ECDSA. This is kind of the diagram of how this works. But there are different ways to validate signatures. It's not just one of the algorithms that is called ECDSA. There is this EIP 1271, which is the signature verification for smart contract wallets. Now, if we think of externally owned accounts, they have their own way to verify the messages or like the transactions that are going through. The smart accounts that are built by code, they have their own way to verify, to have signature verification, right? So this is a standard for verifying signatures on behalf of the smart contracts. This ensures interoperability and security for contract-based signature validation. The use cases are kind of the same that I mentioned earlier, validating signatures for transactions and actions that are initiated by the smart contract. Whatever we code via functions to do something, this is how we validate. This is with what we validate those actions. Then you can do the multiple signature wallets, having multiple parties signing up, and also the identity verification. The key components are the isValid signature function. This comes like a template, right? So the isValid function is like a template. It has these different parameters in place, such as hash and signature. The hash is the data that is signed, that we checked on the diagram, and then the signature to be verified. And then there's this static value that gets returned if the signature is valid. That is kind of pre-configured in the EIP 1271. So to get back to the idea of the first byte signature that I was mentioning it for the hot and cold wallet, this is how we implemented. This is how we enabled our smart contract to be able to receive a different signature, that the first byte will be allocated for the information if that the transaction that is coming in is coming from like the hot wallet or a cold wallet. So this is the same function, isValid function. In this case, what we are doing in here on the left side, we are checking the length of the signature. The length of the signature should, if we wouldn't have the first byte earlier to check, if we would not integrate or like develop this use case, the signature length usually is 65 bytes. But now we know that we want to add another byte to it. So we have to ask if that signature that is coming in is not 66 bytes, then do your thing. Get that to be 66 bytes, etc. We check the format of the signature that we are receiving. This is kind of a value, default value in implementation of the smart contract natively that is kind of successful. It says if the format is good. No, the opposite. If the format is not good, then return this, which rejects the transaction. And then in here, we have to kind of, since the format that we mentioned earlier of the ECDSA signature, that is also part of this EIP, right? We need to see the RS and V values, and we need to place all of these values have different sizes of the signature in bytes. So the first 21 bytes, the second, the 41 bytes, and then the 42 bytes. All of these moved by one because the first byte is being used for the check on the actual wallet. Then we go in here, we do that implementation. We have an if statement saying that if the signature's first like byte is 0, then if recovered address, which we got it from here, is not a hot wallet, revert. Else, if it's not a cold wallet, revert this one. So in this case, whenever we call the function to see if the first signature is 0 or not, this is what is running behind the scenes. Okay. The EIP 1271 signature format, as I mentioned earlier, verifies that CDSA signature has the correct length. It has the values of its components, such as RS and V, fall within the expected ranges that I mentioned earlier in this like assembly code in this part. And if any of those checks fail, this function returns false. Otherwise, if it returns true, indicating a valid signature format and non-malleability. And yes, this was it when it comes to different types of signatures and how to verify different transactions. Definitely, when you go through the code, it will make more sense because you are actually able to touch it and to write the actual functions and pieces. But since today we have released a new version of the documentation and the page that is called Community Code, we are introducing a smart account class via ZA-Sync Guiders, and that one will help you to write, for you to not be the one who writes all of this code yourself to implement a smart account. We have implemented utility classes that will make your life easier when you want to implement different signature schemes. And for example, the ECDSA signature and also the multi-sig example for in this case that we have like use case on our docs is given as utility classes. You don't have to implement it yourself from scratch. And that is lowering like the number of codes from 25 to like 5 lines of code, of course, because it's abstracted away in a way, yeah. But yes, I would invite you to, while this QR code is about the ZK-Sync, I think, events, but go to the ZK-Sync devs, also the docs that I shared on the chat, and let me do this. Yeah, I will not open the other page, but I can maybe stop sharing the screen now, or I will leave it just a little more for you guys to see. Let me see questions.
Yeah, Albiona.
It's again repeating. Yeah. I will maybe stop sharing the screen and we can chat. Okay.
There seems to be a few questions in our chat. Long has requested that you share the record again, if that's possible. And then, is there a specific wallet that you would recommend for for this particular
you.
exercise, should they not have one set up yet? And then there's a
Um,
question from Gautam as well around whether this should be your main wallet or a burner one.
Well, the first question, in this case, if you
Oh,
go
I
through
think
the
you might be
docs,
on mute. I don't know if anybody else can hear you.
can you hear me, guys? Can someone else
Yes,
say
Selby,
something?
we can hear you.
Yeah, we can hear
Okay.
you.
Yes. Okay, awesome. Thank you.
So you might need an account. To kind of give you like a very short overview, with ZK Sync, you're able to build an account. So in this case, I encourage you to have a wallet, Ethereum wallet, and that wallet will be the same that you can use on ZK Sync development. In this case, when you go through the tutorials, you will be able to test things on Sepolia testnet. So you might need to get some funds over there. I can share Sepolia testnet if we are on the same group, so you can all kind of hit me up with, or even send me a DM. But then you might need that, you will need that address for you to be able to deploy on ZK Sync network. So it's not like having a smart account to be able to code. It's just like you will have your externally owned account, normal Ethereum account, to be able to do something on ZK Sync, like follow a tutorial. And the second question was, I forgot. Let me see the chat. I'm confused on how to get started. Let me send you the docs. I don't have a wallet at all. Here. One second. Docs.